analysis that has been done. One of the case studies are performed based on a rather weak subtransmission grid in the northern parts of Norway, which is connected to the main transmission grid, and there are lines and there are loads, there are some villages, fishing villages and so on, and especially one place here where it could be critical. So in this case, a lot of analysis has been done using these methods that we talked about. And yeah, I don't think I'm going to all kinds of details, but the idea is to simulate an increasing load. So the green curve is also always sort of the load impedance versus time. When the load increases, the corresponding power is here. And we see that the indicators after sort of an initial period, they indicate fairly much the same. And they are also able to sort of, all of them are quite precise when the load approaches what would be the maximum the maximum power transfer. And that we also can see here that this is the estimated maximum power transfer. And you see here in the beginning they estimate a little bit too high margin, but as the load approaches the maximum, also the estimate is approaching the right point, and they cross at the same time here. So at the time of maximum power transfer, they are fairly correct. And the other, I just showed the indicator. This is the S-set indicator, and versus time, and versus indicator versus impedance. Okay, another similar study in the southern part of Norway related to the Oscillation corridor, but I show more of this because this is running in real time. But it shows more or less the same. One difference here is that it seems like the method based on the topology information is not accurate when it comes to comparing impedances, and that illustrates the fact that the impedances is not always a good indicator, but the margin computed by the S-set indicators on the other are quite accurate. Another point to make is to simulate a contingency and see what the indicator does then. So in this case, we are running steady, and then we have a line outage, so that the Thevenin impedance is much higher than before, and this is the estimate and the load and the maximum loadability here, and this is more details on the various method. Again, it looks like they do cross at the same time, but not always exactly at the maximum power transfer. So to sum this up, this is implemented in a prototype, also the same as here, implemented in LabVIEW software, and it runs not on this computer, but because it's connected to the PMUs in in the high voltage transmission grid in Norway. So it measures the two line on the Hasle corridor that I have talked about the days many times this week. So this application then connects to the PRL, and which connects to the PDC, which connects to the PMUs in that area. And we have implemented all these curves for the indicator and the voltage versus power and the trend curves. So some results during normal operation. See that we have fairly good margin here. The point is up here. It's a little bit higher here. It also works when there is a transient. You see, during a transient, you will see that the operating point is not exactly on the projected curve, and that's just an indication that there is a transient condition. And you also see in this case that it's quite highly loaded, so it starts to be sort of critical, but it's okay. And we also implemented the other methods, the CT methods, and sometimes that works fine. Sometimes the CT method is not dependable. Sometimes it's really bad, like here. So we believe that our method is better. Okay. This is some examples, the more zoomed in. Low demand, you're operating here. Higher demand, this moves a little. Even higher. You see now the trajectory is indicating that you have a rather weakened grid here. And this is also at a high demand, but with a little stronger grid. Unfortunately, there hasn't been a collapse yet, so I couldn't show you sort of on this side. There has also been tested on more like a sub-transmission grid at the 132 kV network. The same kind of results, basically. Done simulations on the well-known test system for voltage stability, the Sigre Nordic 32 model, which is trying to sort of, what this model is good at is to simulate approximately what happened when there was a voltage collapse in southern Sweden and Denmark in 1983 and in 2003. Some similar things happened, which was that the grid was weakened in the north and in the south, and resulted in cascading outages and collapse of southern Sweden. And these could be replicated in simulation, and the results show that if they had had an indicator like this, they would have seen that already at this point. Here, they would have seen that the system is in trouble. It has already reached the maximum loadability, but they kept on running the system until it collapsed over here. So this is to indicate that this indicator is useful, because it could have given them time to shed load to avoid the collapse if they had that information at that point. So that's the main message on this one. Here's some more detail on that. I'll skip that. Even more details. Something that could have been done if you shed the load. Skip that. Okay, so then I move from voltage stability to angle stability, and detection of power oscillation or characterization of power oscillation or damping. What I talked about yesterday or the day before, I don't remember, was that one method of identifying the frequency and damping of power oscillation was to use the Prony method. If you don't have access to, in that case, if you don't have access to a power system simulator and the ability to do modal or eigenvalue analysis, you could simulate the disturbance and track the ring down of the disturbance, and based on the ring down you could identify parameters of a exponentially damped sinusoidal signal and compute the frequency and damping of that signal. When we talked about it yesterday or the day before, we talked about simulation and studies. But the same thing could be used in online setting, we think. So the purpose here is trying to develop an application that, based on a stream of measurement, capture any kind of disturbance that result in some kind of ring down, and then analyze it. And we know that this happens. There are many examples from the literature where there has been disturbances, and the damped oscillations, sustained oscillations, or even increasing oscillations that led to collapse. So if we can catch this, capture this and analyze it very quickly, then we believe that we have a method that is very well suited to work together with the methods that I also talked about yesterday, that is based on ambient signals. Because when you use ambient signals, you need quite a long time window to estimate with good precision the frequency and damping of your signal. If you capture such a ring down, you can do it very fast. And that is the point. And this is sort of to underline what I said. If you use ambient data, you can try to identify a filter and fit that to the output so that you identify the frequency and damping, for example, of a second order system. If you're able to do that on ambient data with some kind of accuracy, you have a power oscillation monitoring algorithm. With this, this takes time. So the question is is it able to detect the ring down itself and compute the magnitude of oscillations and the damping based on that, and then give very quickly alarm to the operator that something is happening so that they can take action. This is like an example of measurements from basically a normal operation. It's 4,000 seconds, so that is half an what is that? 60 seconds, 4,000 seconds. How many minutes is that? There's a few minutes. So something happens. I mean, even though it looks, this is a completely normal time series of something, from time to time there is something that happens. And if you look closer into it, here for example, there is something that creates certain ring down. Also here, certain ring down, even though this seems to be very well damped. So the clue is, can we capture this and analyze exactly the ring down? And the difficulties in that is maybe mostly related to how you capture exactly the period that you want to analyze. So here in this application, we have used a wavelet to estimate the oscillation magnitude. And slide this through the measured window to find the oscillation magnitude. And thereby, it's easy to isolate that point. And if you have isolated that point, you can take a few seconds from this and analyze that. That is the essence of this algorithm. You could also think of other methods. This is another method which also works. It sort of defines the maxima and minima of the curve and estimates the peak of the magnitude, and it uses that point in time to select the window. And then what it does when the time series come running, okay, here if you zoom in like this, the result of the algorithm is that this is the captured signal. It starts here, and this looks like something that can be analyzed, right? And this signal has a frequency on 0.554 hertz, damping 15%. Magnitude 65 megahertz. Megawatts. And that is easily computed with the Prony method. And this is also implemented in an application in the same way. And this is just an example of real measurements with the power transfer here of around 600 megawatts. 560 here, 600 here. And you can almost see that there are some dominant frequencies here, but not always so much that you can analyze it. But sometimes there is a disturbance that creates a ring down, and that is captured over here. And in this case, this captures something at 0.44 hertz and damping of 10%. So this pops up now and then when something happens, and should be able to give the operator sort of a confidence of the damping of the system. So this was to show an alternative way of do power oscillation monitoring. Then I said I had another application, a little more special one, but related to protection. And that is about identification of the location of faults in what we call the coil compensated networks. What is a coil compensated network? It's a network typically in Norway at 132 kV level or 66 kV, where you have certain transformers from the high voltage level, from 400 kV, for example, down to 132. And all these transformers have a secondary Y configuration and the connection to ground, and they are grounded through this coil. Okay? If it's not good to see. I guess it could be, I mean, on this side it could be either star or delta, but this one is, and this is called a Peterson coil. It's a German guy who invented it a long time ago. And I saw you, some of you were familiar with this, and you would then know that a main reason for doing it like this is that you limit the earth faults. You actually create, when you have you can think of the lines as having some charging capacitances, right? And if there is a single phase to ground fault, you keep this grid almost in resonance, so that if there is a fault here, there will be almost no current. And that is, well, it has its pros and cons. The advantage is, of course, that you don't have high fault currents. But the backside of it is that it's very difficult to actually see when you have a fault, and where the fault, and especially where the fault is. You can measure, of course, the I0 here, the zero sequence, and see that there is a fault, but you don't easily know where in the network it is, even though you have relays in here. Since there is no fault current, there is no relays that trips the fault. So in any case, it would be good to know, for the operator to know where the fault is, so they don't have to disconnect every line to isolate the fault. So that is where we have tried to make an application. If you have PMUs at both ends, of the line, you can do something. Okay, so in this case we assume that we have PMUs at all the nodes, which I guess we will have in the future, and that and then we can make an algorithm. If there is no fault, you can consider the line as with its charging capacitances and you can measure at both ends of that line. If there is a fault, you can think of that as there being a resistive or relevant connection to ground. Like this. So how does, since there is no fault current that of any reasonable magnitude, the current here and the current there will still be kind of normal. But if you look at the differential current, if you look at the difference, if you measure the current up at one side with 1 PMU and simultaneously measure the current on the other side of the line with the PMU and take the difference, that is somehow representing the impedance to ground, right? So in normal operation, that differential current has an angle that is close to 90 degrees. But if there is a fault, the angle will reduce to something nearer to 0 degrees. And that is how we can detect the fault on that line. And we have made some mapping of this in terms of angles and distance as well. And we find that the angle between the feeding voltage and the differential current is a function of actually the fault location as well as the fault resistance and the loading. So that can be used as an indicator both that there is a fault and where it is on the line. So you can actually map the phase angle as a function of where it is on this line, and thereby have a clue of where it is. So thereby you can see the location. And then you could make something like this. When you measure the differential current and the angle is up here, you're perfectly safe. When you are here, there is something, but when there is something wrong, when there is a fault, you are down here. So by that you can make an identification, and you can set up an equation to tell you where along the line, if it's here or over here or here, the fault is. What K is? It's a variable representing the distance from the node. So when K is 1, the fault is over here, and when K is 0, the fault is over here. So that is, so